lecture 11 of our series on numerical methods in civil engineering, we are going to talk about iterative methods for eigenvalue extraction. And at the end, if we have some time left over, we are going to introduce methods for numerical solution of nonlinear equations. Last time we looked at the eigenvalue problem and ways to solve the eigenvalue problem, basically ways to find the eigenvalues and the eigenvectors. And we found that one way to do it was to write out the characteristic equation of the system and then to find out roots of that characteristic equation. But for an n by n matrix, we know that the characteristic equation is a polynomial of order n, and since it is a polynomial of order n, it is going to have n roots. And we talked about Abel's theorem, which tells us that for a polynomial of order greater than 4, it is not possible to get closed form solutions. So, we have to rely on some numerical method for solving the characteristic polynomial. Probably the most widely used method for calculating eigenvalues is what is known as the power method. So, this is an iterative method where we repeatedly start with an arbitrary assumption, for the eigenvector, and we repeatedly iterate using our coefficient matrix to improve the guess to the eigenvector, and can be shown that after repeated iteration the initially chosen vector, it actually converges to the eigenvector. For instance, let z0 be an arbitrarily chosen initial vector, and let us form a sequence of vectors which is given by zk plus 1 is equal to a zk and so on and so forth. So, from z1 from z0 we get z1 by taking the product of z0 with a, from z1 we get z2 by taking the product of z1 with a, and so on and so forth until we get zk plus 1 is equal to a operating on zk, where a is the coefficient matrix, the matrix for which I want to find the eigenvalues and the eigenvectors. Now, for the sake of let us assume that A has n linearly independent eigenvectors and a unique eigenvalue of maximum amplitude lambda I. So, A is a non-singular matrix, it has linearly independent eigenvectors and it has eigenvalues such that the largest eigenvalue is unique, that there are no other eigenvalues which are equal to lambda 1. So, lambda 1 is strictly greater than lambda 2, but lambda 2 may be greater than or equal to lambda 3 and so on and so forth, but lambda 1 is the largest eigenvalue is unique in the sense that there are no other eigenvalues of the matrix equal to lambda 1. So, that is what we assume, and since we have assumed that A has linearly independent eigenvectors, that means if we consider the eigenvectors of A to be x1 through xn, we know that x1, x2, xn form a basis for the vector space of dimension n, right. So, it forms a basis for the vector space of dimension n. So, any n dimensional vector can be represented as the linear combination of my basis vectors, which are x1, x2 through xn. So, for instance, the zk vector, the z vector after at the kth iteration, I can write it as a linear combination of x1 through xn. I could write it as alpha 1, alpha 2, alpha 1 x1 plus alpha 2 x2 plus alpha n xn, where alpha 1 through alpha n are some constant. Similarly, I can write any vector in the iteration zk minus 1, zk minus 2, any vector in the iteration, I can write it as a linear combination of my eigenvectors which are linearly independent. So, we can write, then in that case we can write zk is equal to this. Why can we write that? Well, zk is nothing but ak a to the power k operating on z0, right. a to the power k operating on z0, a operating on z0. So, a operating on zk therefore can be written as a alpha 1 a operating on x1 plus alpha 2 a operating on x2 plus alpha 3 a operating on x through alpha n a operating on xn. And since x1, x2 and xn are eigenvectors of a operating on x1 is nothing but lambda times x1, where lambda is some eigenvector of a. Similarly, a operating on x2 can also be written as some other line eigenvector times x2 and so on and so forth. So, ak operating on zk can be written as alpha 1 times lambda 1 to the power k times x1 plus alpha 2 lambda 2 to the power k times x2 and so on and so forth, where lambda 1 is the eigenvalue corresponding to the eigenvector x1, lambda 2 is the eigenvalue corresponding to the vector x2 and so on and so forth. So, in that case we can write zk like this taking out lambda k outside. So, we get lambda 1 to the power k times alpha 1 x1 plus a sum of these sort of terms where we have quotients of the subsequent eigenvectors with my initial eigenvector lambda 1 raised to the power k. So, basically I am dividing each of these terms by lambda 1 to the power k. And what do we know about these terms? Well, we know that lambda 1 is my largest eigenvector, right. So, each of these terms lambda j by lambda 1 must have modulus less than 1. Therefore, as I increase the number of iterations, as I increase k, as I increase the number of iterations, this term, since this is less than 1, it becomes smaller and smaller, and as it becomes smaller and smaller, eventually this part goes away, this part becomes negligibly small as k increases, and we can see that as k increases, the direction of zk tends to that of my first eigenvector, which is z1, provided of course this coefficient alpha 1 is not equal to 0, right. Thus, the ratio let us look at the ratio zk transpose a zk. What does that become? Divided by zk transpose zk, therefore zk tends to lambda 1 to the power k times alpha 1 x1, because this term goes to 0. Therefore, zk transpose is nothing but lambda 1 k alpha 1 x1 transpose, right. A zk is nothing but again another lambda 1 k, another alpha 1, but now I have a operating on x1, right. So, this is the numerator, and the denominator I get lambda 1 k alpha 1 square x1 transpose x1. So, these terms cancel out, lambda 1 to k cancels out, alpha 1 square cancels out. So, I eventually get this term which is equal to lambda 1 and is known as Rayleigh's quotient. Is that clear? So, a x1 is nothing but lambda 1 x1. So, lambda 1 is a scalar, it goes out, x1 transpose x1 cancels out. So, I am left with lambda 1. So, this ratio, so the idea is that if I start with an initial vector, right, and I keep on iterating on that initial vector. I start with an initial arbitrary vector, I operate each time on that initial vector with my coefficient matrix A, I get a series of zk's, right. Eventually, when I take enough number of zk's, I am assured that if I compute this this product and this product and divide them together, I compute the Rayleigh's quotient, I am going to get my largest eigenvalue, which is lambda 1. If mod of lambda 1 is less than 1 or mod of lambda 1 is greater than 1, star may become 0 or unbounded for large k, and the zk may no longer tend to x1. Why would this happen? Well, take a look at this. If lambda 1 becomes smaller and smaller, lambda 1 is less than 1, as k increases, this term becomes smaller and smaller. So, it may so happen that this term may become almost 0, right. So, in that case zk may not, we are saying that zk tends to, it looks from this that zk tends to x1, but in case this term goes to 0, zk would actually tend to 0. Similarly, if lambda 1 is greater than 1, in that case lambda 1 to the power k, if k is sufficiently large, would become very large. It will become infinitely large for a sufficiently large number of iterations. In that case also zk would not be, it would not be tending to x1. So, what do we do to solve that problem? Well, in order to do that, we normalize. In order to ensure that the scheme does not break down, it may be necessary to scale the sequence zk to ensure that its norm remains bounded. That is, every time we, we compute a new zk, we normalize it. We compute its norm, divide each term in the vector by the norm, and we get a vector with a unit norm, right. So, this we get the sequence. So, instead of working with the sequence zk, we work with the sequence yk, where the norm of yk is equal to 1. So, now my equation has changed, my iteration algorithm is slightly changed. So, zk plus 1 is no longer equal to a operating on zk, it is a operating on yk, right. And therefore, the Rayleigh's quotient also automatically changes. It becomes yk transpose a yk transpose yk. It is clear from this expression that this is going to be bounded. Why is that? Because the norm of yk is 1, norm of yk is 1, a has finite norm. So, this can never be 0 or never be infinity. Similarly, if instead of using the power method on my original matrix A, I use the power method on my matrix A inverse, then instead of getting the largest eigenvalue and the largest eigenvector, I will get the smallest eigenvalue and the smallest eigenvector. Why is that? Because if A has eigenvalues lambda 1 through lambda n, A inverse has eigenvalues 1 by lambda 1, 1 by lambda 2, 1 by lambda n. That should be clear, right. If we do a spectral decomposition of A, it becomes that we get a diagonal matrix, it becomes lambda 1 through lambda n on the principal diagonals. If we invert that matrix, invert a diagonal matrix, then what we have is another diagonal matrix, but now the diagonal terms are 1 by the original diagonal terms. So, A inverse is going to have eigenvalues 1 by lambda 1 through 1 by lambda n. So, we are trying to find. So, instead of using A, if we use A inverse, then we are going to get the eigenvalue which has the largest 1 by lambda term, right. So, that means that will be the smallest lambda term, smallest eigenvalue of A, right. So more generally if we form a sequence, instead of using the matrix A or A inverse, if we use A minus lambda star I as my coefficient matrix, then we get a power method with a matrix A minus lambda star I inverse, right. So, this is going to be my new coefficient matrix. In that case, what am I going to get? In this case, this matrix has eigenvalues 1 minus lambda star. So, it is going to be largest for that eigenvalue which is closest to lambda star. So, if I want to calculate, if I am given a coefficient matrix A and I am given some arbitrary number lambda star, and I want to find the eigenvalue of A which is closest to lambda star and the eigenvector of A which is closest to lambda star, then instead of using A or A inverse, I will iterate with A minus lambda star I inverse, in which case I am going to get my eigenvalue. Then in that case I am going to maximize this term, right. And when do I maximize this term? When lambda becomes as close as possible, when I get the eigenvalue which is as close as possible to my constant lambda star. So, I am going to get the eigenvalue which is closest to lambda star and the corresponding eigenvector. So, the power method can be generalized. It can be generalized not only to compute the first, basically we can use the power method not only to compute the largest eigenvalue, the smallest eigenvalue, we can use it to compute any eigenvalue or eigenvector, right. But the fact that, but one might ask that, well, if we choose lambda star such that lambda star is very close to an eigenvalue of A, right. In that case, this term is going to become very large, right. but won't the problem become won't the problem become singular? Well, that is true, but it will not in general affect the accuracy of my corresponding eigenvector. I am still going to get my corresponding eigenvector corresponding to that eigenvalue with sufficient accuracy. So, that was the power method. There are another class of methods for computing eigenvalues and eigenvectors which are based on similarity transformations. So, what are similarity transformations? Well, similarity transformations are typically transformations of this form, where we operate on a matrix A with another matrix P and its inverse P inverse. So, there is a broad class of methods for extracting eigenvalues and eigenvectors which are based on similarity transformations. In our last lecture, we saw that if P is a non-singular matrix, then the matrices P A, P inverse and A have the same eigenvalues. We proved that last time. So, this can be shown again it is easy enough to show. So, we can this is clear if we look at the characteristic equation of P A, P inverse and A. What is the characteristic equation of P A, P inverse? It is determinant of lambda I minus P A, P inverse. What is the characteristic equation of A? It is determinant of lambda I minus A. Why is lambda the same? Because they have the same eigenvalues, right. So, I can write determinant of lambda I P A, P inverse as basically determinant of lambda P, P inverse minus P A, P inverse, P, P inverse being I. So, in that case I can write this as determinant of lambda P, P inverse. So, if I take out P, P, P inverse minus P A, P inverse, I take out P outside. So, I get P lambda P inverse minus A P inverse. I take out P inverse to the left. So, I get determinant of P times determinant of lambda I minus A times determinant of P inverse, right. So, just because taking into account the idea that the product determinant of the product of two matrices is the product of its determinants. Determinant of A B is equal to determinant of A times determinant of B, right. So, and we also know that determinant of P is equal to 1 by determinant of P inverse, right. So, determinant of A is equal to 1 by determinant of A inverse. So, these cancel out, this determinant of P and determinant of P inverse cancel out, and I get determinant of lambda I minus A, which means that P A, P inverse and A have the same characteristic equation, and we know that our eigenvalues are nothing but the roots of the characteristic equations. So, the eigenvalues have to be the same. Also, since P A, P inverse operating on P x is equal to lambda P x, right, again this should be obvious, P inverse P is I. So, we have P A x operating on lambda P x, but again A x is nothing but lambda x. So, this means that P x is an eigenvector of P A, P inverse, right. P x is an eigenvector of P A, P inverse. So, we in similarity based methods for extracting eigenvalues, we perform a series of similarity based transformations with orthogonal matrices that will therefore leave the eigenvalues unchanged while transforming the eigenvectors as above. We know that if P is any non-singular matrix, then it leaves the eigenvalues unchanged and it transforms the eigenvectors like this, right. Now, we are saying that instead of using any non-singular matrix, we are going to use only orthogonal matrices, right. We are only going to use orthogonal matrices and orthogonal matrices will also therefore leave the eigenvalues unchanged while transforming the eigenvectors as above, right. Assumption is that I am using an orthogonal matrix with it is non-singular, right. Orthogonal matrix always is non-singular, its determinant can only be if it's orthonormal, its determinant is plus or minus 1, right. So, sequence of matrices, what we are doing is that we are repeatedly operating on A using a similarity transformation, but a transformation matrix is an orthogonal matrix, right. So, we start, so we obtain a sequence of matrices starting with A0 equal to A, we operate on A0 with a similarity transformation using Q, we get A1, we again operating on A1 with the similarity transformation Q, we get A2, and so on and so forth. So, AK is nothing but QK transpose AK minus 1 QK, where QK transpose QK is equal to I, right. It is an orthogonal matrix, K is equal to 1 to 2, and if X is an eigenvector of A. So, we so the only criteria is that this transformation matrix be a orthogonal matrix, right. At each step we can use, if we want, a different orthogonal matrix, but we are using a orthogonal matrix for each similarity transformation. So, x1 is nothing but q1 transpose x. Why is that? Because I know that my eigenvectors are p times x, right, p times x. So, q1 transpose x, x2 is equal to q2, qk. Similarity transformation means that my eigenvectors are the original eigenvectors times the transformation matrix, right. What is the matrix here? Here it is q transpose. Why is that? Because my similarity transformation is of the form P A P inverse, right, or in case of an orthogonal matrix it is P A P transpose, right. So, P A P transpose. So, instead of P I am using Q transpose, right. So, instead of my eigenvectors are going to be transformed as Q transpose operating on X, right. So, X1 is equal to Q1 transpose X, X2 is equal to Q2 transpose X1, which I do, if I expand it out, I am finally going to get QK transpose QK minus 1 transpose QK minus 2 transpose, so on and so forth, times X. So, after K similarity transformation, my original eigenvector X is going to be transformed to this. So, in that case I can just, by doing a transpose of both sides, I get X is equal to Q1 Q2 through QK operating on XK. The sequence similarity transformations also by definition perform symmetry. Why? Because we can show this AK transpose is equal to QK transpose AK minus 1 QK transpose, which is equal to QK transpose AK minus 1 QK. Thus, if the initial matrix A0 is symmetric, the sequence of similarity transformations will yield a symmetric matrix. So, as we do our transformation, if we start with a symmetric matrix, we are going to get symmetric matrices. The orthogonal transformations used in practice are mainly of two types: plane rotations and reflections. So, usually what people do, there is a very well known method which we are going to talk about later on, known as Jacobi's method, which basically just uses plane rotations. There are other transformation techniques which use reflections. So, we operate, so our transformation, orthogonal transformation matrix is usually a rotation or a reflection. So, we repeatedly operate on my original matrix A with repeated rotations or repeated reflections until I get a diagonal system, which has the eigenvalues on its principal diagonals. So, the orthogonal transformations used in practice are mainly of two types: plane rotations and plane reflections. The aim of both types of transformations is to reduce the initial matrix to as close to a diagonal form as possible, with the eigenvalues occupying the diagonal locations. You can think of it like this: you know that when you have a symmetric matrix and you have linearly independent eigenvectors, you can transform the symmetric matrix to a diagonal matrix by operating on the symmetric matrix with a matrix whose columns are my eigenvectors, right. So, if I have a matrix A and which we looked at last time, right, and we have another matrix X, and each column of X corresponds to an eigenvector. If I do X transpose A X, I eventually end up with a diagonal matrix whose principal diagonal elements are my eigenvalues, right. So, here we do not know a priori what are my eigenvectors, right. So, I am by using this repeated similarity transformations, I am trying to get as close as I can to my eigenvector matrix, right, and then eventually I am going to get a diagonal matrix which is going to contain all the principal values, meaning eigenvalues on its principal diagonals, right. So, what is a so I said that we repeatedly operate on this matrix using orthogonal transformations, using plane rotations and plane and reflection. So, what is a plane rotation matrix? A plane rotation matrix is a matrix in the PQ plane which is equal to the identity matrix except for the elements on the pth row and qth row, pth column, and qth row and qth column. So, only it is an identity matrix except for the elements R P P. So, the intersection of the P row and the Q column and the P row and the P column, right, only those terms are going to change. The rest of my terms are going to remain 1 and 0 like my usual identity matrix. So, only terms which are going to be different are R P P, R P Q, R Q P and R P P, and these will be like a plane rotation, right, which you know a plane rotation matrix is like your matrix cos phi, sin phi, minus sin phi, cos phi, right. So, in this case we have that on our P intersection of my pth row and P and Q columns. Similarly, qth row and P and Q columns. So, those are, and then we have control over the rotation angle phi, right, which is less than phi. So, the idea is to give a plane rotation, to choose these phi's, to choose this rotation, choose these phi's, meaning choose this rotation matrix such that it tries to annihilate the off diagonal terms of my original matrix. What do I want? I have an original matrix, right, which has got off diagonal terms. I want to get to a diagonal form where my diagonal elements occupy the where my eigenvalues occupy the diagonal elements. So, what do I want to do? I want to annihilate my off diagonal terms. I want to make them 0. So, I can choose my phi's. So, I am going to choose my phi's in these each iteration. I am going to choose my phi with a target to annihilate a particular off diagonal term. And how am I going to choose which off diagonal term to annihilate? Well, the natural choice is I will try to choose the off diagonal term which is largest, right. The largest off diagonal term I will try to annihilate. In it, at any iteration k, I will choose my R matrix R k such that it will try to make the largest non off diagonal term 0. And if I do this sufficient number of times, turns out that I can, in most cases, I can annihilate all my off diagonal terms, and I am left with a diagonal matrix. And since I know that my similarity transformation leaves the eigenvalues unchanged, those eigenvalues of a diagonal matrix, that diagonal matrix has the eigenvalues on its diagonal, and those eigenvalues must be the eigenvalues of my original matrix, right. So, if this transformation operates on the matrix A, so it only changes the elements of the pth and qth. So, if I form a matrix R like this with only the RPP, RPQ, RQP and RPP different from 1 and 0, then it is going to only change the elements on the pth and qth column of A. Similarly, if we operate on A with R transpose, if I form R like this, but then instead of operating on A with R, I operate on A with R transpose, I am only going to change the pth and qth rows of A, right. So, I can change the pth and qth rows or the pth and qth columns. So, that was about plane rotations. What about reflections? Well, for reflections, the transformation matrix has this form. It is of the form P depends on a particular vector W, and the P of W is I minus 2 W vector product W, right, tensor product, right. So, it is basically the outer product. It is when you take a dot product of two vectors, you get a scalar, right, but this is not a dot product, this is a vector product, or sorry, it is not a vector product, it is a tensor product, right. It is a tensor product. So, basically if you think of it like this, if you have a vector, if you write a vector in row form and then you write a vector in column form, if you take the product of the row vector with the column vector, you end up with a scalar, right, that is your dot product. But instead of that, if you take the vector in the column form and then you take the product with another vector in the row form, then you end up with a matrix, right. So, it is changing the order, right, you are going from one order to two orders. So, it is called a tensor product, right, it increases the order from vector we go to matrix, right. So, omega W. So, we are saying that if we construct P to be I minus 2 W tensor product W, or if we forget tensor, we say outer product, 2 I minus 2 W outer product W, with the condition that W is a vector of unit norm, that is W dotted with W is equal to 1. This matrix is an orthogonal matrix. Why is this matrix an orthogonal matrix? We can show that if I take the transpose of this matrix and take the product of that matrix with its transpose, I am going to get an identity matrix. Well, you can show that. I am not going to go into too many details of that, but it is obvious, right. So, you can just see that if we take this, right. So, first term is going to be I, the second term is going to be, so this operating on this is going to be 4 W tensor outer product W operating on W outer product W, and this is going to give me minus 2 W outer product W operating on I. This is going to give me another minus 2 W outer product. So, this is going to give me this part and this part using the operation of using the rules for tensor products. We can write W tensor product W operating on W tensor product W as W tensor product W times W scalar product W. Since W scalar product W is equal to 1, so we are going, these two terms are going to cancel out and we are going to get I. So, the transformation matrix is orthogonal if we construct it like this. If we take any vector W of unit norm and we construct a matrix by I minus 2 W tensor product W, we are going to end up with a orthogonal matrix. It also we'll show later that it also leaves a symmetric matrix symmetric, right. So, it preserves symmetry. But what it does is that when this operator operates on A, on any matrix A, it basically reflects the matrix A in the hyperplane through the origin which is orthogonal to W. So, we consider then that space, in that n dimensional space, since we are considering an n dimensional matrix, as space is n dimensional. In that n dimensional space, I have an n dimensional vector W which is suppose passing through the origin, and I have a plane which is orthogonal to that vector W in that n dimensional space. And what this transformation does on A is that it reflects the matrix A in the hyperplane through the origin orthogonal to W. So, that is why it is called a reflection matrix, right. You can think of it like this, minus W tensor product W operating on 2. So, it takes out the projection. So, you can see from here it takes out the part of A in the W direction twice. So, that is what gets reflected, right. It gets reflected about the hyperplane through the hyperplane passing through A with orthogonal W. PW is also symmetric. Well, that can be shown trivially again using the properties of outer product. The transformation A transpose PWA thus transforms each column of A independently according to this. So, A operating on this P operating on A is nothing but this P operating on each column of A, where AK represents a column of A, and again using the transformation rules for outer products operating on vectors, we can show that this is equal to this. Similarly, if I instead of using P operating on A, if I use I operate it from the right hand side, right, instead of operating on A with P from the left hand side, I operate on I operate on A with P from the right hand side. I transform each row of A, right. So, one of the most widely used similarity transformations for obtaining eigenvalues and eigenvectors of symmetric matrices is known as Jacobi's method, right, as I mentioned a little while earlier. So, Jacobi's method, we do a series of similarity transformations using orthogonal matrices Qk, where Qk are plane rotations and they are used to transform A so that it finally becomes a diagonal matrix. In the kth step of the classical Jacobi's method, we search AK for the largest, I am sorry, this is a typo, this should be the largest off diagonal element, right. We search for the largest off diagonal element and then I construct my P matrix, taking care to choose my angle phi in such a manner that my largest diagonal element becomes 0, right. I annihilate my largest off diagonal element becomes 0. If this largest off diagonal element is A P Q K, then we make a similarity transformation A K 1 is equal to R P Q transpose R P Q, where R is a planar rotation, right, which transforms just the P and Q columns of A, right, where angle phi is chosen so that A P Q K plus 1, right, after the transformation K plus 1 is reduced to 0. So, repeated use of this scheme leads to annihilation of all of diagonal elements, and finally, we get a diagonal matrix with the principal values of A comprising the eigenvalues of A, comprising diagonal elements, and since diagonal elements have to have the eigenvalues, those are the eigenvalues of A, right, because I know that my similarity transformations leave my eigenvalues unchanged, right. Sometimes it is not possible, it is not generally true that by doing a finite sequence of similarity transformations we are going to get a diagonal matrix. It does not work out that way, it does not work on all the time. So, in that case what is the second best option? Well, in that case, instead of trying to get a diagonal form, we try to reduce it to as simple a form as possible, right. We try to reduce it to as simple a form as possible, and then using that simple matrix we construct our characteristic polynomial, right, characteristic polynomial, and then try to solve the characteristic polynomial numerically, right. So, we know that if we directly solve the characteristic polynomial of a large matrix with lots of components, then we are susceptible to ill conditioning, right. We saw that last time, because the characteristic polynomial is susceptible, is very sensitive, right. Minor perturbations in the elements of A can lead to large changes in the eigenvalues, right, if we try to obtain the eigenvalues after solving the characteristic polynomial. So, for a full matrix it is not a good idea, we saw, to use the characteristic polynomial approach and try to find the roots of that polynomial. However, if we reduce that full matrix to a sufficiently compact form, to as close a diagonal form as possible, then in that case the characteristic polynomial is not as susceptible to ill posedness, right, it is not as ill posed, right. So, in that case we can go ahead and solve the characteristic polynomial to find the eigenvalues, in case we cannot reduce A to diagonal form just by performing similarity transformations. So, what are some of these forms? So, we try to transform the matrix A to some other compact form which can be obtained in a finite number of steps. Such forms include the symmetric tridiagonal form for symmetric matrices and the Heisenberg form for non-symmetric matrices. Then once we have obtained the symmetric triagonal form or the Heisenberg form, we go ahead and write the characteristic polynomial for those simpler matrices and solve them to obtain eigen. So, what are symmetric? Symmetric diagonal matrix is of this form. So, you can see it is pretty close to a diagonal matrix, although it is not exactly a diagonal matrix. So, doing transformations, we can reduce any symmetric matrix to symmetric diagonal matrix, symmetric matrix, non-symmetric matrix to Heisenberg form, and then we can use the try to write down the characteristic equation for this, characteristic polynomial for this, and try to find the roots of that equation. Okay, so now we are going to change tack and try something else. So, up till now we have focused on solution of linear systems, right. We have looked at a variety of linear ways to solve linear systems. We have looked at convergence, we have looked at error propagation, we have tried to find out which are the best possible ways, most efficient ways of solving a linear system. So, now we are going to switch over to nonlinear systems. In many civil engineering applications, we encounter nonlinearities. For instance, we have nonlinear material behavior, whether in solid or fluid mechanics, we encounter nonlinear material behavior, or for finite strains or finite rotations, we encounter nonlinear kinematics, right. So, in that case, the nonlinear physical phenomena gives rise to governing equations which are nonlinear, right, which are nonlinear. For instance, if we have a matrix A, to give the simplest possible example, if we are solving for Ax equal to B, where the coefficient matrix A is a function of the solution, right. So, A is a function of x, A depends on x, right, and we are trying to solve Ax equal to B. So, every time the solution changes, my coefficient matrix is also going to change, right. Every time x changes, my coefficient matrix is going to change. So, it is no longer a linear system, it is a nonlinear system. So, how do we solve those systems? Well, many of these equations cannot be solved analytically. So, we have to solve most interesting problems, cannot be solved analytically unless they are the simplest possible problems with the simplest possible nonlinearities and the simplest possible geometries and things like that, simplest possible material properties and things like that. We cannot solve them analytically. So, we have to solve them numerically. And if we have to solve them numerically, we have to find the roots of nonlinear equations, right. We have to find the roots of nonlinear equations, and the roots of nonlinear equations cannot generally be expressed in closed form. We have seen that before. So, numerical methods based either on linearization, basically we take our original nonlinear system and we linearize it. In the first class we introduced some basic ideas about linearization. We are going to talk about it in greater detail later on, but we can use either linearization or successive approximation to solve these nonlinear equations. So, these iterative methods start from an initial approximation to the root and produce a sequence which eventually converges to the desired value. However, nonlinear equations may have multiple roots. What are multiple roots? Well, we will talk about that and we will give precise definitions of multiple roots later on, but I just wanted to mention that we can have simple roots and multiple roots, and we will define what exactly are simple and multiple roots later on. But unless the starting value of the iteration is within a certain interval, say that contains the root, the iteration may not converge to the desired root. So, for instance, suppose I have a nonlinear function like this and I want to find the root of this nonlinear function, root meaning the value I want to find the value of the abscissa for which my ordinate becomes 0. So, I want to find x such that f of x becomes equal to 0, right. So, I want to find this x, right, such that f of x becomes 0. But if I restrict my iteration interval to between a and b, where a and b do not bound the root, I have no chance of finding the root, right. If my root lies outside my iteration interval a to b, I have no chance of finding the root, right. So, I better make sure that my iteration interval bounds my root, right. So, my root lies within my iteration interval. So, many algorithms, if the root lies within an iteration interval, however large be the iteration interval, my iteration interval can may be as large as I want, right. But if my root lies within that iteration interval, it is not this situation, but it is this, but with my a b far apart as far as possible as I want, but still those methods are going to, after suppose n large number of iterations, they are going to converge to the root, right. Come hell or high water, they are going to converge to the root somehow, right. But there are some other methods which are not going to converge to the root unless I start sufficiently close to the root, unless my interval is bounds the root, that is a relatively narrow bound on the root, right. And the problem is that most good iteration methods, good iteration methods means methods which converge fast to the root, which have fast rates of convergence, they need a small initial interval. So, that means that they converge faster near the root, right, but far away from the root they do not perform well, right, they converge slowly, right. So, for the most efficient methods, they work best near the root. So, unless the starting value of the iteration is within a certain interval, say a b, that contains the root, the iteration may not converge to the desired root. Other algorithms may require initial approximation that is close to the root in order to converge. These methods typically have the advantage that they converge more quickly. So, what is a good alternative? Good alternative may be to start with a method that maybe does not because we do not know the interval which bounds the root, right. So, but we only know that the root lies somewhere between a and b. A and b is big, right. We start with a and b big, right, and then we use our relatively unsophisticated method to narrow the bound, right, and then we use our sophisticated method near the when the bound is sufficiently small, right. The sophisticated method means more expensive, right. So, I do not want to use my sophisticated method when my bound is large. So, I use my relatively unsophisticated method to narrow down that bound, right, and when I have a sufficiently narrow bound, when I have reached somewhere here, then I can use my sophisticated method, because that is because I know even though I am using the sophisticated method and it is more expensive, I know that it has very good convergence properties. So, I am going to converge faster to the root. Okay. So, then when the iterate gets close to the root, it may be desirable to switch to an algorithm which converges only for starting values close to the root, but converges much faster. So, I said I am going to define what are simple and multiple roots. So, let me do that. Alpha is said to be a simple root of this equation f of x is equal to 0 if f prime of alpha is not equal to 0, that is at alpha the derivative of f is not equal to 0. So, that is f does not have a stationary value at alpha. Alpha is said to be a multiple root to the equation f of x is equal to 0 if with multiplicity q greater than 1, if we can write g of x is equal to x minus alpha to the power minus q times f of x. That is, we can write f of x in terms of another function g of x times x minus alpha to the power q, and in that case we say that f has roots alpha with multiplicity q. That means there are q roots of x equal to alpha, right, and this function g of x remains bounded as x goes to alpha. So, as x goes to alpha, g of x does not become 0 or infinity. So, g of x has some finite, g of x is a finite, has some finite value, right. If this condition is satisfied, we say that f of x has roots, has multiple roots alpha of order q, right, q multiple roots, q multiple q roots alpha. So, we will focus mostly on iterative schemes. So, while looking at our algorithms, we are going to first look at algorithms for one dimensional nonlinear equations, because they are the easiest to understand, right, and most of those ideas which we obtain for one dimensional nonlinear equations get generalized to multiple dimensions, but we are going to look at multiple dimensions later on, but the basic ideas we are going to see with one dimensional nonlinear equations. Multidimensional nonlinear equations, what do I mean when I say multidimensional? It means that there are more than one independent variables, right. Instead of just x, there is a vector of independent variables x1, x2 through xn, right. So, multidimensional nonlinear equations give rise to a system of nonlinear equations. For instance, if we have nonlinear equations in variables x1, x2 through xn, it is clear that we need a system of equations. For one variable I need one equation, right, for n variables I need n equations. So, I need a system of equations, and that I can represent as a vector. F now becomes a vector, f of x equal to 0. So, I want to find the roots, I want to find alphas, a vector of alphas such that f alpha becomes equal to 0, where now alpha is a vector, and I can write this as f1 f2 fn equal to 0. So, this is the system of equations. So, solving a multidimensional system of nonlinear equations is considerably more difficult than solving a one dimensional nonlinear equation, which should be sort of obvious. However, many of the methods for solving nonlinear equations in a single variable are easily generalized to multi-dimensions. However, they all assume that the methods that we are going to talk about, they all assume that good approximations to the roots are known. If no prior information about the location of these roots are known, the problem becomes considerably harder. We shall discuss techniques for solving nonlinear problems such as full Newton-Raphson, modified Newton-Raphson, and quasi-Newton-Raphson. However, I should mention that there is no technique, no nonlinear technique, right, which can claim that given any nonlinear problem it is going to be able to solve it, right. So, that I am not aware of any such technique till now, but we have better techniques and not so good techniques, but there is no technique which can solve all nonlinear problems without fail, because nonlinearities are really hard to handle. So, in our next class we are going to talk about the most efficient methods for solving one dimensional nonlinear equations. We are going to talk about the Newton-Raphson method. We are going to look at the Newton-Raphson method very closely. We are going to look at its convergence properties, right. Then we are going to look at the second method, its convergence properties, and then we are going to move on to more general methods. Thank you.